To our Thursday Informatics Conference of the Department of Medical Informatics and Clinical Epidemiology at OHSU, which has continued as it used to in the Big Theater and now virtually, and maybe someday we'll be back to the Big Theater in the not too distant future. It gives me great pleasure today to introduce our speaker, Dr. Mohammad Adibuzzaman, or as he prefers to go by, Adib. Adib is one of our newest faculty members in the department. He's been here a little under a year, and he has another, in addition to being a faculty member, has an important role at OHSU as co-director of the Biomedical Informatics program of OCTRI, the Oregon Clinical and Translational Research Institute. So he splits his time, or really actually spends most of his time leading the OCTRI Informatics program, but he also is a member of our faculty. And one of the reasons why I wanted him to speak is so other faculty and students can get to know his work a little better and look for opportunities for collaboration, mentoring, and so forth. So in addition to his OCTRI co-director role, he is an assistant professor in the Division of Bioinformatics and Computational Biomedicine of the department. He has a PhD from Marquette University in computational sciences, also has a master's degree. Originally got his bachelor's degree at the Bangladesh University of Engineering and Technology in computer science and engineering. He spent a number of years at Purdue University, and then we recruited him to OHSU, and that's where he is now. So he's going to talk today on the topic of informatics systems and methods for evidence generation in medicine. And as always, we will record this. It will be posted to our YouTube channel. It will, and he will give his talk. People are free to post questions or comments in the chat. He'll leave some time for discussion at the end of his talk. As always, people are encouraged to keep their cameras on, although it is the lunch hour, and some people may turn their cameras off while they eat their lunch. So go ahead, Adib.
Thanks so much, Bill. Can you hear me? I see my slides.
Yes, we hear you fine.
Awesome. So thanks for the kind introduction, Bill. This is a little bit awkward to give presentation in Zoom or WebEx, but I'm trying to getting used to it. So for today, I will talk mostly about my journey from a computer science background in healthcare or medicine. And so I have like 4 different components in general. The first half is about my background and some why I work in healthcare. And then I will talk about 2 broad areas regarding informatics system and some of the methodological work that I work on. And then finally, I'll also talk about a little bit about the informatics work that we are doing at OCTRI that I co-lead with Dr. Shannon McWinney. So starting with my journey into informatics and epidemiology or clinical epidemiology. So this is, Bill already did a very good summary of my background, but as Bill mentioned, I worked, my undergrad degree was in computer science and engineering, and then I had a PhD in computational science. But after my undergrad, I worked as a software engineer for a few years, and then I worked in Singapore as a research assistant for National University of Singapore for a few months, and then came to the US, was working on a PhD at Marquette University on computational science. But during my PhD, I got a chance to work at the US FDA for a few years as an ORISE Fellow, which stands for the Oak Ridge Institute of Science and Engineering Fellow. And that really actually had a deep impact on my trajectory of my career. So I'll talk about that on the first half. And after that experience, I worked at Purdue University Reproducible Center for Healthcare Engineering for a few years. Actually, it's more than 6 years. It's not a very small amount of time. But Purdue is a very engineering and computer science and statistics focused university, but they have a center for healthcare engineering, and I was working there and building these informatics systems and working with collaborators across the campus on developing AI solutions in medicine. And then I was recruited at OHSU like October 2021. So I've been here for around almost 3.5 months now. And as Bill mentioned, I have two different hats. One is the OCTRI co-director of informatics and the assistant professor of DMICE. So I will start with some of the projects that I worked at the FDA, and then highlight how I got into these two areas of research that I'm working on the informatics systems and methods. So the first project I worked at the FDA was developing a algorithmic system to predict hemorrhage, or to detect hemorrhage or predict acute hypotensive episode from blood pressure data. So for that particular study, we were given animal study data. So these animals were anesthetized and they were taking bloods from these animals. And then they were monitored for all of their vital signs at a very high frequency. So they were collecting data at 1,000 samples per second and looking at heart rate, blood pressure, pulse oximetry, pretty much everything you can think of. So my project was around, can we look into this blood pressure data and can predict acute hypotensive episode or detect hemorrhage early enough so that we can make interventions. And that is particularly important for human health because in a mass casualty situation or traumatic injury cases, it's very difficult to identify acute internal hemorrhage or blood loss. And if you can do, but there are some treatments and you can intervene early. So this was a US Army funded project at the FDA. So what we did, we looked into the blood pressure data, as you can see in the first, in this figure. The x-axis represents the time and the y-axis represents different vital signs. And the zero red vertical line indicates the starting point of the hemorrhage. And as soon as the hemorrhage starts, the two things generally happen. One is the systolic blood pressure decrease, but to compensate the loss of blood volume and maintain the tissue perfusion, the body reacts in a way so that it actually increases the heart rate to compensate the blood loss. And that's what you see on the left-hand side figure, the heart rate is also increasing. But at some point, the body cannot take it anymore and it just collapses and the pig actually dies in this case. So we were looking at this blood pressure data and we used a Markov chain simulation model. So basically what we did was we divided the blood pressure into different stages and tried to identify how these state changes, the transition to different states changes in terms of the blood pressure as the hemorrhage progresses. So with that, this is just a sample example. We had 3 different states in this case, and we computed how each of these samples from one range moves to the another range, and it is a moving window. And over a 20-second window, do we see any change in system dynamics in terms of the Markov chain that would give a different pattern as the hemorrhage progresses? And we found that the second largest eigenvalue of the Markov chain with a specific parameter, mixing rate, we call that mixing rate, gives a pretty good indication of progressive hemorrhage. And we could detect hemorrhage pretty early. And this is the figure that you see here at the bottom, mixing rate. And that shows that change pretty quickly. Like within few minutes, we could identify that there is a change from all the different animals. So this is one example, but we did a statistical test with 9 different animals, and this worked pretty much with every case. But while working on this project, and I'm referring to this project because this was one of the motivating projects that I worked on. But while working on this project as a PhD student at the FDA, I spent almost 2 years during my PhD time to set up this high frequency 1,000 samples per second data into a supercomputer and have all this software installed and run this simulation where we are generating like thousands of images for pattern recognition and validating those with the statistical tests. And I thought like it was they were taking a catheter, they put some catheter and then they're just taking the blood from the animals. If that answers to your question. So as I was saying that I felt like I spent a ton of time on the system development rather than on the actual algorithmic question. So one thing I wanted to do was build a different or better system where developing those high performance environment for a PhD student or researcher should be pretty simple, and they should not spend a huge amount of time on how to set up the data for analysis. So that is one area that I focused later on in my work at Purdue. And then I also worked on another project at the FDA, and this was on evolution of machine learning algorithm for risk-benefit analysis. And this also led to one other areas that I worked on later in my career, which is the causal inference techniques. So this particular study focused on one specific algorithm development for prediction using different algorithms like decision tree, support vector machine, neural network, and many more. So we looked into one research question, which is, how do we predict medical emergency team activation criteria, which is a criteria of 3 vital signs falling into different categories that would indicate a rapid decline in health status. So if the heart rate increases or falls below certain range, this criteria is triggered and an emergency team actually goes to resuscitate or help the patient. Same with systolic blood pressure or oxygen saturation. So in this case, this medical emergency team activation criteria was triggered because if you look at the target window, and this was actually to the best of my recollection, was a contest or a challenge. So here, the first window, x-axis, between 0 to 60, this is the observation window. And then the idea is, can you predict by looking at this observation window data, just these 3 vital signs, and we do not have access to this gap window, which is 60 minutes after the observation window, but we'll also only have the data 10 minutes after the 60 minutes of the gap window. And within that 10 minutes, we have to predict whether there will be a MET activation criteria triggered or not. So in this case, the oxygen saturation falls below 85% saturation level, and that was one of the criteria for MET activation. So this was a true positive event. And we trained this algorithm with hundreds of patients' data from Mimic database, and then we developed these machine learning algorithms. And as you can see, we have reported 2 different algorithms, decision tree and support vector machine, and we used different training size with different cross validation. So the first 4 is like we have a training size of 500 patients, but we have 4 different splits. And then we also tested with a training size with 1,000 samples with 2 different splits, and one case of 1,500 samples for training and another case of 200 samples per training. That's what you see on the x-axis on the box plots. And then we reported the sensitivity and specificity and all other machine learning algorithms, matrices for those different training sizes and random splits. And we found that there is a pretty wide variety for those sensitivity and specificity with the same data, but with different random splits and different random different training sizes. So one question we were very interested in was, how do we explain this variability of machine learning in a transparent and explainable way? And I had been thinking about this during my PhD, and then I focused one other research area, which is the causal inference using graphical models. And that also is a theoretical work that I explored at Purdue University. So going forward, from the takeaway message from my experience at FDA with these two projects, where I wanted to explore in these two areas, like how do we develop informatics systems for easier exploration and visualization and computational systems that would expedite the translation piece. And also, once these algorithms are developed, how do we explain this and understand this in a transparent way for risk-benefit analysis and communicate that with the clinical experts? So as I said, so this is the big research agenda that I was working on going forward since I started at Purdue. So we have all these different types of data, AHR, genomics, imaging, wearables, and most of these data are big data, but they are called biased data or observational data because of confounding and other reasons, selection bias as well and other reasons. But at the same time, historically, we rely in medicine on randomized controlled trial data, which are considered experimental data or good data. And traditionally, the regulatory bodies like FDA rely on that kind of data for evidence generation in medicine. So the question is, how do we actually combine these two different types of data, both technologically, informatics system-wise, and methodologically to complement randomized controlled trial to expedite randomized controlled trials, or even in some cases, do virtual randomized controlled trial with observational data set. So these are the two broad areas that I had pursued. And I'll talk about these two areas in the next few slides. So the first area is the big data system for reproducible research. And the idea here is that if we want to develop a cloud system or HPC system that would integrate all these different types of data like genomics, laboratory prescriptions, electronic health records, wearables, administrative data like insurance claims, and we have many different stakeholders like researchers, industry partners, patients, physicians, and government research agencies, and policymakers as well. So for that kind of environment, if we think about this is a very large data system, what type of features or characteristics that we want in that system? And we listed a few here: reproducibility, shareability, data governance, IRB and data use agreement protections, privacy of individual patients, security, data aggregation, data management, audit trail of different data usage, computational system management, like hardware usage, research applications, and for different researchers that are very different from one another, and sustainability and maintenance of that kind of system. So I've been working in this area for a while, and this is a huge area, and there are many industries and many companies that actually have made significant inroads in this area. But in my humble opinion, I think this is still in its infancy about what can or needs to be developed for a large-scale data aggregation platform in the cloud or in the on-premise system. So to develop that kind of system, on the right-hand side, the figure that we see here, I broadly specify this as 4 different types of layers. The first is the infrastructure layer, which is the computing, storage, networking, security, and those traditional big data or data center management type of infrastructure. And then the second module is the data preparation and load, which is includes the identification, data standardization, and each of these areas are actually a large area that a lot of people have been working on in different ways. as an example, standardization for electronic health record is a huge area, but this needs to be integrated with other sources of data, and standard methods and tools and protocols needs to be developed for other types of data as well. The third module I refer to as the analytics environment, which is we want to support the researchers with an open and modularized architecture so that we can support different programming languages, reproducibility, data provenance, shareability of code, where we can share the code, but we can test the hypothesis with a different data set. And as the data is evolving and changing, how do we keep track of versions of data and reproduce previous results for a better consensus on research projects or research results. Access management, I have this as a privacy preserving layer in that infrastructure system. And IRB, data use agreement, audit trail, de-identification, privacy preserving record linkage, all of these are part of that layer of systems. And finally, the applications are the clinical applications or the AI applications or even research applications. So there could be clinical decision making as well as publication focused applications or AI model development. So that should be in the final layer. It could be real-time or offline applications. So as I said, this is a huge area. And what I started was as a prototype environment development, I worked on a project for module 3, which is develop an analytics environment in an open architecture for reproducibility and provenance with programming language agnostic interface. So this is what I worked on that area. So we developed a open source software stack with Hadoop, Kubernetes, Jupyter Notebook, and different open source technologies to integrate electronic health records, data or claims data, insurance claims. So if you look at the Hadoop file system storage layer here, we have HDFS and CSV files were used to store that type of data. Excuse me. We looked into 3 different types of data to be linked in this system. One was electronic health record or claims, which are structured data, waveform data, which is physiological parameters that was captured during the hospital stays, like heart rate, blood pressure, usually high frequency, and also image data like echocardiogram or MRIs. And then on the computational layer of that system, we used Spark MapReduce for in-memory computation. But to get the data from the Hadoop file system within the Spark in-memory system, we used different database abstraction layers for different types of data, like HBase for NoSQL data, Hive for SQL type of query within Hadoop system, and Hippie for image processing. And on top of all of those, we had a service layer that was deployed within Kubernetes cluster. And we deployed Jupyter Notebook environment within Kubernetes cluster, but that could be extended with patient viewers, dashboards, and GUIs within the same environment. So researchers would only interface with the Jupyter Notebook environment, and they can pull the data and do advanced analytics or computation from all the layers down and without having to think about much about infrastructure management or setting up the data into the HPC system. So that research prototype project actually became a campus-wide initiative at Purdue University. We hosted multiple large EHR and insurance claims data into that environment. And there were like around 100 people, including faculties and students, who are using that system. It had around 300 terabyte data storage and around 70 million patient data from different sources across the country. And most important of those was the Cerner Health Facts, which was the EHR data from all of Cerner's hospitals across the country for around 20 years of that. And we used multiple research publications with these datasets, and some of them are still ongoing. The next area I wanted to talk about is not about informatics systems, which is on the AI or causal inference side. So as I said, one of the motivators for me was how do we develop a prediction model that would explain the reasoning about the predictions for the algorithm for safety and risk benefit analysis, as well as for better understanding of the underlying clinical or biological process. So in that area, we were looking into one particular framework called structured causal model, which is a graphical model. And this is a relatively new theoretical development that's been pioneered by Judah Pearl from UCLA. And the idea is that all the variables within a problem domain needs to be represented in a causal diagram, and the causal diagram will dictate what variables needs to be adjusted for confounders, and that can be used for a virtual randomized controlled trial so that we know exactly which variables we want to intervene and identify the bias and also adjust for or remove those biases. So the biggest challenge of that project or that framework is actually how do we come up with the causal diagram in the first place? And this is an open problem in this area. And the other traditional approaches of causal inference, which is propensity score based model, also look into the same potential outcome framework, but they don't use causal graph. Rather, they use propensity score to identify what to adjust for and what not to adjust for. But the strength of this graphical model is that you explicitly define what all of your assumptions are, and then it becomes easy to compare objective evaluation of your methods versus the other methods. But the challenge here is, again, how do we come up with the causal graph is an open problem. So we have been working on one project that to reproduce randomized control trial result from observational data. So this particular study was motivated by some landmark studies. The first one, so there was a research question about whether hormone therapy has an impact of chronic heart disease in a very large randomized control trial. This randomized control trial was one of the largest in the history of randomized control trial. And this was initiated by Women Health Initiative. And they found that the benefit, there is a risk of hormone therapy using for chronic heart disease using that trial. But an observational study found that this is actually beneficial. And then Harnan et al. Used propensity score-based matching and showed that this actually aligns with the randomized control trials, this is still harmful. So the question is why there is a mismatch between RCT and observational data. So Harnan actually established this research method, one of the landmark studies. He showed how this can be done with observational data. So we attempted to reproduce this result using the graphical causal model. But as you can see on the right-hand side of this figure, the study of the randomized control trial study and the observational study were significantly different in terms of length of the study, follow-up period, and some other characteristics of the data. So how do we characterize all of these mathematically similar to a randomized control trial and look into the same measures for outcome for objective comparison. So we are still actually working on this project, and right now what we have done is we mapped each of these studies in terms of the population characteristics and treatment allocations or interventions and the actual query with a graphical causal model. And now we need to look into the actual data. We are working on identifying, completing the data use agreement to get the raw data and reproduce the results. So this is a theoretical work that we are ongoing, and the eventual goal is, again, how do we use observational data to reproduce clinical trial quality evidence from observational data. The other area in the causal inference, other topic that in the causal inference area that we are working on is how do we come up with the causal graph in the first place? So this is an ongoing work as well. And the idea here is that we will use different structured learning algorithm and physician input or domain knowledge expertise, as well as literature data that is published in high quality journals, and then iteratively develop the causal graph and provide mathematical validation and experimental result of the graphical model to find the confidence in the graph that we develop. And this is an open problem, and this is one of the main reasons that this graphical model has not been adapted for more clinical research, because developing the graph is pretty difficult in the first place. So the idea of this framework of different sources of knowledge embedding into the causal graph actually comes from the hierarchy of knowledge in medicine. So as we know that systematic reviews or randomized controlled trials have higher quality of evidence compared to observational data. So we wanted to use that hierarchy to develop a causal graph generator engine that would automatically incorporate all these different sources of knowledge into a causal graph with inputs from the experts. So right now we are working on this framework. This is an ongoing work that we are working on a publication right now, and a proposal is under development for this work as well. So again, the idea is we are looking at 3 different sources: expert knowledge, data, knowledge from data, which is in the form of a structured learning algorithm. And also the third one is the peer-reviewed literature. So we are incorporating all these different sources of knowledge for a specific query and generate the causal graph systematically, and then evaluate that with some simulation models. So that part was pretty much about my research activities. And on the other hat that I wear as the co-director of informatics at OCTRI, I'll talk a little bit about that as well. So at OCTRI, informatics, I think that might be of interest to, and you all of you know about this informatics program much more than I do, because I've been here only for a few months. But at OCTRI Informatics, we care about publications and research grants and community partnerships, industry engagement, and investigator satisfaction for all of our informatics-related work. So we want to support the community for faculties and students to have better metrics in terms of these variables. So this is what I'm working on right now. This already exists to many extent, but I'm working with Dr. Shannon McWhinney to come up with a cohesive strategy for research data warehouse that usually supports our research activities at OHSU. So at the bottom layer, we have supporting communities. That is the research community that we support, but we also want to support startup and innovation for technology transfer, those activities, workforce and training, and computational approaches that different faculties work across the campus. And we are trying to make that RDW, or Research Data Warehouse Management, in a way so that we get input from different consortiums that we are part of, like OCHIN, N3C, ODC. Of course, OHSU is a big development partners in terms of a big database and IRB data that we maintain. SDOH, social determinants of health for different communities that we partner with. Night Cancer Institute is one of the largest community that we work with, and also develop partnerships across the region and across the technological companies. So to achieve that, the big idea is that data, EHR, social determinants of health, imaging wearables, that would be at the heart of what we do at the informatics program. And the technological solutions, that is the informatics systems, to maintain the data in a way so that it would support privacy, standardization, interoperability. We want to develop that in a way so that it becomes a vehicle for partnership and innovation as well. And the other side of that value generation from this data comes from the application of different methods, which we need to partner with biostatistics, DMICE, and other faculties across the campus, so that this wheel of innovation can actually speed up the commercialization, grants, publications, those matrices. And finally, for OCTRI, because we are a clinical and translational research institute funded by NIH, our eventual goal is to show the translational impact, which we can see in terms of the clinical trials, or health metrics improvement in the community, or number of pragmatic trials, or outcomes of pragmatic trials. For OCTRI, we also have other programs like biostatistics, evaluation, navigator community, and we are trying to build the synergies with those other programs for better investigator support. We already do all of those things. I'm not saying we don't do any of those. So I'm just trying to work with Dr. Sharon McWhinney for better cohesion with those other groups for better investigator support. A quick summary of what we have in the RDW data. So we have around 4 million patients from OHSU since around, I think, 2005 or 2004, because that's where we have a better EHR system implemented. And mostly we have electronic health records, but we are looking into other partners to look into other types of data and bring into RDW. So that is not in place yet, but that's the strategic plan that we are developing. And here is another view of the RDW dataset that is increasing as patients. We have more patients over the years. So right now, we have almost 4 million patients in the RDW data. So I'll stop here, but before I do, I want to thank my collaborator, Anant Gama. He's a professor of computer science, so he was my primary collaborator on the informatics system. And Professor Elias Berengoem, he was my primary collaborator on the causal inference side, and is a professor of computer science at Columbia University now. And another student that I want to mention, his name is Riddhiman. He's a graduate student that helped in many of those works that I have done. And many others collaborators that I don't have the space or time to talk about today. So I'll stop here and get it back to Bill. If you have any questions, I'm happy to answer. And thanks for listening to my talk.
Great, thank you. Are there any questions out there? If not, I'll actually, it might be more of a comment than a question. When the Women's Health Initiative was published, it was a big deal around this campus because there were many fervent views. And I think, as most people in the audience know, DMICE stands for Department of Medical Informatics and Clinical Epidemiology. And the clinical epidemiology part of the department has been involved in systematic reviews on many topics related to women's health, including hormone replacement therapy. One of the one of the explanations, so the people who were on the less favorable side of hormone replacement therapy argued that one of the problems with the observational studies is a bias, a socioeconomic bias, and that before the Women's Health Initiative study was published, there was a women of higher socioeconomic status who were healthier, had higher incomes and better health care and all that. And so that kind of, it was, in fact, someone, a former faculty, she's actually retired now, Linda Humphreys, some of you may remember her, actually published an analysis looking at that and found indeed that that was a big confounder with the observational data. On the other hand, there are some faculty, people like Jeff Jensen in the Department of Obstetrics and Gynecology, who actually argue that the formulations given in the Women's Health Initiative studies were not the optimal ones. There was this kind of time concern, which I think you're getting at in this slide. How did those things kind of play into the data set that you're using, and how will it help you, uncover, or how might we uncover the truth going forward?
So the idea of this exercise is to show that all of the comments that you mentioned can be represented mathematically into this graphical model, and then we can do a mathematical query which can be implemented in a computer system or AI engine and can be answered automatically. So the biggest puzzle here is, how do we embed all this information, which is in this particular example maybe represented as selection bias as a socioeconomic factor for the observational study, and we can represent that into causal graph, and then we have to adjust for that into this causal query based on the graphical structure. So if there is a confounding pathway versus a collider or other pathways, then this needs to be adjusted. But if it is as a mediator, then we don't need to adjust for. So that should be derived by the causal structure, and often cases that is not discussed in traditional observational studies. So I agree with all of those comments, and the part of the research question that we are trying to answer here is that, hey, this is how we represented all of these concerns in a graph-based method, and this is how you can adjust a more objective way, and you can be transparent and explainable, provide this answer, like why we are getting what type of results.
Mm-hmm. Okay. And I see that Chengda had a question, I think, on the same topic. I think you mostly answered that. Any other questions from?
Yeah, thank you for answering my question. So my understanding is that on the observational data from Graustein, that analysis was like univariate. They only analyzed, did not consider any confounders. And on the third column, that was they were considering other confounding factors.
They did those adjust for those confounders, but it was not in a very systematic way. And then Harnan et al. Actually showed that using propensity score, you can better identify those confounders and identify what are the variables to adjust for.
Okay, thank you.
Any other?
Hi, Adib. This is Arvin.
Hey, Arvin.
Great presentation today. That was very illuminating. Thank you.
Thank you.
I was hoping you could go back to, it might have been slide 20, the one with a number of stakeholders, and it has that wheel.
Yeah.
I was hoping maybe you could kind of elaborate a little bit more about Let's see if we can get there.
Here.
Yeah, that one. You know, just kind of talk about, I know some of it you've already covered, but talk a little bit more about how the technologies there towards the center might, perhaps there's been identified texts at some of these other institutions that you named there, OSU, PNNL, how those are kind of interrelated, or if there's any specific examples and how that
Yeah.
kind of generates out, if you don't mind.
Yeah, of course. This is a very good question. So I will give one example first, which is more concrete, and then other examples, which is a little bit open-ended. So the first one, let's say we want to integrate different types of data, EHR with electronic health, wearable devices or some other SDOH data, like death from the Oregon Health Authority or something else. So if this data is already de-identified from each of these sources, how can you still do record linkage? Or if it is not de-identified, how can you still keep the privacy preserved record linkage? So there is a company called DataVant, and they actually commercialized this idea about privacy preserving record linkage using some hash techniques from each of these HIPAA PHI identifiers, and that is being used for some of those health information exchanges across the country. So as an idea, we can partner with DataVant, but if there is any new techniques developed in this area of privacy preserving record linkage, that can be an opportunity to partner with that company for licensing and commercialization purpose. But that is just an example, it doesn't have to be that
Right.
example. Beyond that, we know that Microsoft, Amazon, and Oracle actually bought Cerner recently, as you know, which is one of the largest EHR vendor in the country. And all of these tech companies are trying to get into healthcare side. And part of that is providing that cloud solution where you can integrate and develop a platform with all these features that we talked about at the beginning, which is this one. And each of these areas, if we have some innovative ideas from our faculties and students, we can work potentially with these companies to develop some technology transfer, or we can support individual faculties develop their own startup companies as well.
Right.
So if it makes sense to you.
Yeah, absolutely. That's terrific. I love the vision. Thank you.
Thank you.
Great. Any other questions? Comments? Okay, well, we can give people a little bit of their day back. I want to thank Adib for presenting, and I hope that faculty and students who have been listening in can you know, if they have anything that overlaps with Adib's interests, be in touch with him. And of course, through OCTRI, there's a lot of potential data for people to use in their research. So thank you, Adib, and we'll see you all at the conference next week.
Thank you so much. Thanks everyone for giving your time today. Thank you.
Thanks, Adib.